Hey guys, this is Srini and you're watching Python tutorial videos on my channel Python for Microscopists on YouTube. In today's tutorial, let's continue the topic from last tutorial where we've covered histogram based image segmentation, and for that we've used a very nice image where every region that we would like to segment had kind of a relatively uniform gray levels. So histogram based segmentation was possible, and there's no reason to use any advanced tools, if you could do that. Now, if that's not possible, what if you have regions that are visibly kind of different, but then very noisy, or you cannot use histogram to separate them because the peaks in the histogram kind of are not separable? So for these situations, we have various segmentation tools. One of those is called random walker segmentation. You may have done other forms of segmentation, like putting some seeds, creating some seeds, within each region, and then using watershed, for example, to region grow. So there are many ways, but let's look at random walker segmentation in this specific, in today's tutorial. Now, what is random walker? So let me go ahead and open. I searched online and just search for scikit image and random walker segmentation. You'll find this page, and all it's doing is once we define some markers, again, as you can see, the markers are defined in each region of our interest. Once you define that, then it calculates anisotropic or solves anisotropic diffusion equations to calculate the local diffusivity coefficients, okay, and then decides whether that's a specific pixel is part of, let's say, segment A or segment B. If you are a life scientist or material scientist and you don't understand what this local diffusivity is or what anisotropic diffusion is, and by the way, if you're a material scientist, you better know what diffusion is and what diffusion equation is, because I know I have done this a couple of decades ago when I was doing my research in material sciences. If you're a life scientist, chances are you probably do not know what this is, but it doesn't matter. We are going to use this as a tool out of this toolkit. And if it works, great. If not, then what parameters do we change to make it work, right? That's all we need to know as the users of this specific module. And for this exercise, I've actually Google searched for a backscattered electron image of an alloy, and I found an image that looks, you can see it here. And it seems to have two different phases. Again, if you're a material scientist, you know what a phase is. These are, and the dark one is probably a low density phase, and the bright one is a higher density phase. And given that there is not much contrast difference between the two, the user either wanted to collect it this way, or maybe the difference in density between these two regions is not that high, so it's not spanning the entire, it's not covering the entire histogram space of, let's say, 0 to 255 or something. So anyway, this is not an easy to segment data set if you want to use just histogram, because you have pixels within this darker gray region that kind of overlap with this light gray region, pixels in the light gray region. So let's go ahead and get started with the random walker segmentation, and let me fire up my Spider IDE. And as usual, the first one from skimage, import IO. And I'm going to also import image as float, because again, we'll be doing a lot of math with these NumPy arrays. And whenever you do math, we'd like to stay away from rounding errors. So using, converting images as float is almost a must in most cases. And let's also import matplotlib.pyplot as plt, because we'd like to plot our images. Let's also do numpy as np, because I know I'd like to use at least a couple of functions like mean, and something else from numpy. We can remove it if we're not going to use it. And let's start reading our images. And as I mentioned before, I want to read image as float and io.imread. And what are we going to read? A file which is located in images folder, and it is called alloynoisy.jpg. And there you go. We now have our image available. Now, before proceeding, first let's look at the histogram. If the histogram looks great, well, we don't need any other means. So let's plot histogram. And histogram of what? Of our image. And we have to flatten the array, which means it takes the 2D NumPy array and flattens it into 1D so it can plot it. And how many bins do we need? Let's do 100. And the range of our values should be equal to between 0 to 1. That's because this is a float image and our values range between 0 and 1. So when I go ahead and plot the histogram, that is a very horrible looking histogram for an image. As you can see, we can clearly see two regions, when we look at the image, but the histogram has no indication about these two regions. I mean, it's not clear from this image that we do have these two regions. So obviously histogram based segmentation is out of the question right now. We can actually denoise the image and improve the histogram. So let's see if that helps. There are many ways of denoising the image, but we would like to preserve the edges. We'd like to preserve the texture if there is any. So the best textured, retaining filters, nonlinear filters, let's say, median is one of them. And my personal favorite is non-local means. And I have the explanation open here. Non-local means denoising, again, part of scikit image package. And how do we use it? Let's go ahead and copy the sigma and these three lines and then we'll edit this in a minute. And of course, we need to copy the library that we need. So restoration, and let me paste it up here. Okay, so my sigma estimated is NumPy mean, and my image name is img, so I'm going to change that. I do not like to print anything for now, and I can leave the patch size as is. All this is doing is it's creating a dictionary of patch size, patch distance, and multi-channel, and unwrapping it here. So let's just leave it here. Doesn't hurt. So that should denoise our image, and I'm going to just call this _img. And now let's go ahead and let's not look at the image. Let's actually go ahead and plot the histogram. Okay, so I'm going to plot the histogram, except this is going to be denoise _image. So now when I plot it, we should see two peaks, hopefully, because I've done this once before. And oh, it's taking some time. Again, the denoise non-local means algorithm can be very computer intensive, memory intensive. So I try to do fast mode equals to true. Although for this image, you would see slight difference between fast mode equals to false and fast mode equals to true. True tends to overdo it a little bit for certain type of images. In this case, we'll actually see whenever it's done, we'll see a histogram, and then I'll run it again with true, and we'll see the difference between these two. So I'll give it a few more seconds to finish it off, because it's very important for us to see the difference between these two, which clearly demonstrates that there is a difference between the fast mode being turned on and turned off. To me, the image looked very pleasant when I turned the fast mode off. It looked very realistic. When you turn the fast mode equals to true, sometimes it can get a bit cartoonish. You need to be very careful. So you see here, this is much better than the other histogram that we had. Yeah, and this is with fast mode false. Now I changed it to true. First of all, when I run this, you'll see the result within a couple of seconds. That tells you that it's faster, but then at what cost? Yeah, at what cost? The image may look a bit over denoised. Okay, so here obviously I got much better result when I have fast mode equals to true. Both peaks are very nicely separated, so I'm very happy. Now I can actually, it's still not enough for us to use thresholding, because there's a bunch of pixels that fall between these two peaks where we have a lot of overlap. So I can expand the range. I can zoom into between 0.7 and 0.9. But let's do one more thing before we go ahead and do our segmentation. There is something called, let me open, I think I opened the page here. Uh, Histogram equalization, contrast limited adaptive histogram equalization. It kind of equalizes the image, which means the darkers will be darker, brights will be brighter, and this is like adaptive histogram. So I need to import skimage.exposure, and then within that we have so first let's go ahead and do that from skimage import exposure. Okay, so within exposure it contains the functions. So let's actually look at equalized image. Okay, I'm going to assign a variable equalized image is nothing but exposure dot. So there are two, equalized histogram and adaptive equalization. Try both. Equalized histogram tends to be a bit more aggressive, meaning the dark will be too dark, the bright will be too bright. You get like very nice contrast, which is also okay. But let's use this, the adaptive histogram for now. And all we need to do is denoise underscore image, and now denoise image, and let's go ahead and plot our histogram for after equalization. So hopefully we should see some change. Okay, we should see it any second now. That is amazing. Yeah, so now all it's doing is it's taking this histogram and actually stretching it out all the way down to almost 0.3. So instead of between 0.75 to 0.95 or something, now we have it from 0.3 to almost 1. You can clearly see both peaks, but not good enough for histogram based segmentation. So we need to do something else, and that's exactly where our random walker segmentation comes into picture. Okay, so now let's go ahead and start. In fact, for the fun of it, let's look at the image. Let's look at this image, and let me comment this out. So this kind of shows you, it's almost like, looks like a segmented image. Yeah. So if I actually do cmap equals to gray, you'll see much bigger difference. If I actually save it and open the image, you can see that it's not really a segmented image. There are a lot of pixels here, a lot of pixels there. So it's just a equalized image, and that's not bad compared to the input image. Oh, sorry, I never showed the input image. Compared to the input image here, we have improved the histogram. But again, we realize that it's not enough for us to do a histogram based segmentation. So let's go ahead and define some markers and then run our random walker segmentation. So the way we define the markers is we start with an empty array, so filled with zeros, not empty array, but it's an array that is filled with zeros. And what is the shape of this array? The same shape as of our original image. And also let's actually fill this with we call this the data type equals to np dot uint, because we'd like to fill this with the zeros, ones, and twos depending on what type of what markers we have. So and where do we want to put the markers? We want to put the markers inside the regions where we already know we are highly confident, meaning anything below, let's say 0.6, but above 0.3 seems to be a good one for the low end marker. Okay, so let's start with that. So markers, we have already defined the markers, but we need to fill it, meaning what do we want to fill those markers with? With that, what do we want to fill the array with? With all the pixels from equalized image that are less than 0.6. Okay, so all the pixels below 6, I'm confident that they are, but you can also put less than below 0.6 and all the ones that are greater than 0.3. Okay, if you want to be particular about it. Let's do the same for the other one. and that would be equalized image. Sorry about that. Equalized image where it is greater than, for this, let's say 0.8, 0.8, and equalized image less than 0.99. Okay, that should be good. So all we're trying to do is define the markers within these regions, and if you want, we can go ahead and look at the markers. So let's look at these markers. Let me just remove the gray part, and what we want to look at is our markers. Let me go ahead and run it. Now we don't see anything there. Okay, and why do we not see anything? Let's go ahead and do some investigation. Markers, equalized image less than 0.6, right? Less than 0.6 from this image, and greater than 0.3. That to me makes sense. And oh, we just defined it. We did not say what to fill it with. That's why it's always important to do these sanity checks. So now, I mean, I could have actually looked at my markers here, and then it says all 0 in my variable explorer. Variable explorer can be a great tool for debugging. Okay, so all zeros. Now that I'm assigning this to 1 and 2, let's do this one more time. I hope we'll see something now. There you go. Now we filled this with zeros and twos. Okay, I wonder why 0 and 2. It should have been, maybe it's not showing the entire array. Maybe it's just the first few ones. You know, these are zeros where we haven't defined anything. Yeah, where these are filled with zeros anyhow. So it is filled. I mean, we can see the markers right here. High probability or high confidence regions where that actually falls in this window. It's 1. This window, it's 2. So we are set. We have the markers. So we are all set to do our random walker. And again, the random walker, let's go back. How do we do this? This is part of SK image segmentation. I'm going to copy, go here, SK image segmentation. Okay. So now let's just do labels equal to or random walker. Yeah, we imported that. And which image do we have? Equalized image. And labels, our labels are called markers. Okay, and if you look at it, says beta. I'm going to use beta equals to 10, and my mode equals to, I think by default it is BF as it shows over there. And if you want to know more about beta and BF, I just looked at it. It actually talks about it. Where was it? If you look at random walker, it actually talks about what beta is. It's just a penalization coefficient for random walker motion. The greater the beta, the more difficult the diffusion. Well, what does that mean from image processing? You probably don't have any clue. I don't have any clue at this point. So let's go ahead and run this. And once, if the result doesn't look good, maybe that's one of the parameters we play with. Okay. Now let's go ahead and show the labels. This should look like a segmented image now. That's it. It's done. Okay, let's run it. Isn't that great? In fact, we don't even need to clean the image. That looks very good actually. So let's compare that with our original image. That is great segmentation. We can improve a little bit, you know, in certain regions and play with some of those numbers, but that is not bad actually. This is actually not very bad. I mean, if you want to segment this into like segment 1, segment 2, and you want to combine that, if you remember in the previous video, we have actually done that. So where I called segment 1 equal to, in fact, I am show labels. Let's just look at the image labels. It's 2. So segment 1 equals to, let's just do labels equal 1, and our segment 2 equals to labels. There should be something, I mean, 2 we clearly see it here. I don't see 1. We'll find out why. Okay. Labels. Is it because the? I mean, obviously it's truncating for us to see. That's probably the reason here. So we just did segment 1 and segment 2, and you can actually combine these two. But let's just go ahead and im show. segm1. Okay. So let's go ahead and show segment 1. And that's just again my sanity check. I don't see any ones reported, which is not probable enough, but it is actually showing my segment 1 there. I mean, in fact, if you want to do, you can do CMAP equals to gray, or you can combine these two and just like we have done previously, all segments equals, and let's fill this with zeros, and again I'm creating a blank image and going to fill everything with segment 1 and segment 2 values. So this is what do I want to do? Equal eq underscore ing dot shape, and let's do 0, and the other one eq underscore image, sorry, dot shape 1. This is 3 such channels. Okay. All I did is just created an empty image, and now I want to assign some color. All segments for segment 1, let's just make this red. Well, and the other segment, let's make it green. So all segments segm2, let's call this, sorry about all the typos here, equals 0 1 0. That's it. So now if you print all segments, we should hopefully see a red and green map. So plt.imshow all segments. Let's run this. There you go. We have our red, we have our green, and if we have another segment, that would be whatever color you want to assign it. So this is how you do segmentation if your histogram looks horrible, like we saw earlier. So all we have done, again, just to summarize this, dealing with floating numbers, okay? And then I denoise the image right here. These lines of code is for denoising the image. And then I've done some histogram equalization, because after denoising, initial histogram looked horrible. After denoising, it looked better. In fact, it looked much better if I did fast mode equals to true for non-local means filtering. And then I realized that the range is not broad enough. So histogram equalization may definitely help in extending the range, which it did. Then I realized that, okay, everything below 0.6, I'm very confident that this belongs to the darker phase. Everything that's greater than 0.8, I'm confident it belongs to the brighter phase. So we came down here and kind of mentioned that exactly the same thing. Anything less than 0.6 and anything greater than 0.3, change mark it as 1. Same thing for the other one, mark it as 2. So it actually created the markers, and I used those markers as my markers as part of random walker, and applied it on equalized image with a parameters of beta equals to 10 and mode is BF, whatever that is. And then it created actually the labels image with values of 2 and 1. Okay. Then my markers, by the way, is nothing but values of 0, 1, and 2. Okay. Zeros correspond to unindexed pixels, unmarked pixels, or unlabeled pixels. 1 corresponds to whatever we did here, 2 corresponds to this. Now we don't want that. We don't want unindexed pixels. So we want to segment those ones. That's why we're using random walker, okay, where it walks through the image. Every pixel assigns it either 1 or 2, okay, based on using these markers as the initial seeds or markers. And now we said, okay, we know that every pixel in labels is either 1 or a 2. So if you want to separate these two, that's all I just did here. Segment 1 is labels that all correspond to 1. Segment 2 is where labels all correspond to 2. And then I created an empty array again with all zeros, with the same size, with the same shape of my equalized image, original equalized image. And then everything that corresponds to segment 1, I colored it in red. Everything that corresponds to segment 2, I colored it in green. And I'm just showing it here. Now I can just save this image. I'm done with my segmentation. Okay, so this is how you perform your image segmentation. This is no different than how you would do it on a proprietary software or software like ImageJ, where you do some operation, you know, and then you equalize your image, and then you do something else, you do something else. But here everything is automated. Now I can actually go ahead and use this on many images that look very similar. Or I could have modularized this code by changing the denoising part and everything else. So each time I don't have to write the code, you know, those 3-4 lines for non-local means denoising, for example. I could be creating my own class of all denoising algorithms and then just pick which one I want whenever I want. Yeah, that's a better way of handling your code. But again, we're not software engineers. We just want whatever the task that we want to build for our image processing purposes. I hope you found this tutorial useful, and in the next tutorial, let's learn something new. Thank you very much.